Okay, I think we're ready to restart. So we're pleased to have Sergei Skipetrov from Grenoble, France, doing theory on localization of light by actually cold atom vapor. Please.
Thank you very much. I would like to start by thanking the organizers for putting together this interesting meeting and for resisting the pandemic. So I'm very glad to talk here. My talk, I should apologize also that my talk will be not about the landscape theory, which I still didn't manage to apply to this optical problem, but I hope that this will be done soon. Okay, so we have heard already that Anderson localization takes place for quantum particles, and basically it is described by this Schrödinger equation that I show here on the left. And of course, you can easily realize that there is an analogy between the Schrödinger equation and the wave equation on the right here that describes propagation of light, sound, or any other type of waves. And this analogy becomes even clearer if you think about monochromatic waves at a certain energy or with a certain frequency omega. So in this case, you can rewrite the two equations in exactly the same form, and you can identify the effective potential and the effective energy in the case of light or other type of classical wave. So here already you see that there is a difference between the quantum problem and the optical problem, because in the optical problem, the effective potential turns out to be proportional to the frequency squared, and the frequency squared is also the energy, the effective energy of this problem. So we have now a kind of energy dependent potential, and this has many important consequences. One of these consequences, maybe the most important, is that in the quantum problem here on the left, we can basically be in two trivial regimes. In the first one, the energy is very, very large. And in this case, the electron or other quantum particle is likely to propagate through the potential almost without scattering or with some weak scattering. And in the second trivial case, the energy is very, very low, and the particle is trapped in a local minimum of the potential. So in this case, the localization can take place even classically without taking into account any interference effects. But for light, the situation is different, because as I told you, the effective potential is proportional to the effective energy. We are always in this first situation. So the energy is always higher than the highest maximum of the potential, and we never find ourselves in this trivial situation. So this makes, in some sense, localization more difficult to reach. But at the same time, if you reach it, it should be more easier. It should be easier to show, to prove that it is indeed Anderson localization due to interference effects and not a trivial capture in a local potential well, because this type of situation is simply not possible for light. So there are numerous optical experiments in low dimensional systems like 1D and 2D systems, in which different groups have observed Anderson localization of light. But in 3 dimensions, the situation is more complicated. So in 3-dimensional experiments, people try to follow the road developed first in the studies of electronic transport. So when people do experiments on Anderson localization of electrons, at least the first experiments, old experiments, were just measuring resistivity or conductance of a wire and changing the composition of the wire or the pressure or some other parameter, and observing that at a certain point in the parameter space, the conductivity of the sample goes to 0, which is identified as a metal insulator transition. So there are equivalent experiments in optics, but instead of measuring conductance, people measure transmission of light through a disordered sample. So here, for example, what was observed is the exponentially decaying transmission through a disordered sample, which suggests that the conductance or transmission should be 0 in the limit of very large sample. And this is in agreement with the Anderson localization situation. And in more recent experiments, the measurements were position and time resolved. So the sample was illuminated by a focused pulse, and then the intensity profile, position and time dependent intensity profile, was measured on the opposite side of the sample. And also from that, you can see if the waves propagate diffusively through the sample or if they are localized due to disorder. So unfortunately, both these experiments were strongly criticized from the very beginning, and later on, the same authors, they have performed additional measurements under more controlled conditions, and they have found that the initial interpretation was erroneous, and that that simple interpretations can exist without invoking Anderson localization of light. So given that the experimental observation of light localization in three-dimensional systems remains elusive at the moment. So my work is theoretical, but unfortunately, in theory, the situation is not much better, because these systems which are used in the experiments on Anderson localization of light are quite complicated systems. So typically, these are ensembles of grains, of dielectric grains of irregular shape, as you see in this photograph. And it is very difficult to say what happens with light in the system, even if you assume that each grain is spherical. I mean, even for a single spherical grain, already the cross-section, the scattering cross-section depends strongly on the frequency and features several resonances. And if you put such grains close together, it's very complicated to compute what will happen. So this is why it seems to be reasonable to go to this model system, which is a gold atomic system, in which all these complicated grains are replaced by very small point-like atoms, which are assumed to be two-level atoms. And the advantage of this situation is that we know everything about light scattering by a single atom. So we know, for example, that if we shine light close to some resonant transition, we can forget about the rest of the internal structure of the atom and assume that there are only two levels, and there is only one resonant frequency which has a certain, and this resonance has a certain width, gamma 0. So we only have two parameters. And then the only difficulty that remains comes from the fact that these different atoms do not scatter light independently, and there is a dependent scattering. So as I told you, I will speak about the theory of the systems, but I would also like to use this opportunity to promote the work of Robin Kaiser in Nice, who is working very hard to make this theory real, in a sense, to make experiments on light scattering in strongly disordered and dense atomic clouds, and to observe Anderson localization of light in these systems. But how can we describe this system theoretically? So there are several approaches. I will use probably the most simple one, which was proposed by Foldy and Lax many years ago. And it was first proposed for a different system. It was proposed for sound scattering on air bubbles in water, but it can be easily adapted to light scattering by atoms. And the idea is very simple. So you can write the wave field on the given scatterer here as a sum of the incident wave field plus the fields scattered by all other scatterers in the system. And in this way, you obtain a set of linear equations for the fields on the scatterers. You see this size. Of course, you can easily derive this equation from the wave equation by rewriting it as an integral equation and taking into account the fact that the system is discrete. So you have discrete scatterers. They are positioned at discrete positions. You see that in this equation, the main ingredient is this Green's function of the wave equation that I call G. And moreover, you can define a matrix that I will call Green's matrix, which has elements equal to this Green's function from the position of one scatterer to another. And it turns out that this matrix actually controls everything that happens in the system. So in particular, it controls how the wave propagates and also controls the structure of the quasi-modes. And it can also be generalized from the scalar situation to other types of waves, like for example, for light. What changes is that the expression for this Green's matrix, for the elements of this Green's matrix becomes much more complicated, but it's nothing else than the dyadic Green's function of Maxwell equations, as you see here. And also the size of this matrix increases. Instead of being n times n, where n is the number of scatterers, it is now 3n by 3n, because we have now 3 different polarizations. But besides that, the general framework remains the same. So as I told you, you can find almost anything about this system from this Green's matrix. In particular, you can expand the wave field inside the system in terms of the wave vectors, eigenvectors, sorry, of this Green's matrix. And the eigenvalues, the corresponding eigenvalues, will give you the eigenfrequencies and the decay rates of these quasi-modes. So as you see in this system, the atoms are in the free space. So there is no any reflecting surface that surrounds them, which means that light can leak out from the system freely. And this is why the eigenvalues are complex, with the real part describing the frequency of the corresponding quasi-mode and the decay rate describing the inverse of the lifetime of the mode. So if I diagonalize this matrix for a given configuration of atoms and I plot the eigenvalues on the complex plane, I will see something like this. So here each blue point is an eigenvalue. The number of eigenvalues is equal to the number of atoms in the system. And I can also study the eigenvectors that correspond to each of these eigenvalues. If I do that, I will see that some of these eigenvectors are extended and some of them are localized, as you see here. And this localization can be interpreted as Anderson localization due to the disorder in atomic positions. So up to now, this description was not statistical. So I can do this for any given configuration of atoms, but this doesn't make much sense because in typical experiments, we don't know where the atoms are. So we cannot check this kind of prediction in any reasonable way. So this is why we turn to the statistical description of the system. And this statistical description I will do in terms of the dimensionless conductance, which has been introduced by Dominique today. So Dominique already explained very well the main idea. The idea is that you compare the lifetime of the mode and the spacing between neighboring modes. In my model, it's very simple because the lifetime or the inverse of the lifetime is simply given by the imaginary part of the eigenvalue. So this will be the inverse of the tauest time in my system. And the spacing between neighboring modes gives me the inverse of the Heisenberg time. So if I divide one by the other, I get the dimensionless conductance, and I can perfectly define it for the system where there is no resistance, there is no conductance, there is no currents, but still this parameter is perfectly defined. So when it comes to practical application of this dimensionless conductance analysis to the statistics of the system, there are several issues which were not really detailed in the talk by Dominique. And the issues are that when I do this calculation of conductance, I find a quantity which is random. So you can ask, what should you do? Should you make the average of it? Should you study the second moment or whatsoever? And the point is that people tried different approaches. So it turns out that studying the average conductance is not very useful because it's often dominated by random realizations of disorder in which the conductance is very high. So there are other options, but the most general options is to study the full distribution of conductance. So this is something that I show here on the right. And you see that this conductance has a very wide distribution. So I have to study the distribution of the logarithm of conductance if I want to trace it in a reasonable scale. And also what I show here is quite a special point where you see that distributions corresponding to different sizes of my system, they all coincide for small conductances. And you see, I mean, this is a kind of signature of localization transition. So in the talk of Dominique, this localization transition was manifest in the fact that the dimensionless conductance was independent of the system size. Now, as I told you, because dimensionless conductance is a random quantity, I cannot say that it's independent of the sample size, but I can say that the distribution of conductance becomes independent of the sample size. And to study these distributions more quantitatively, I will use the mathematical objects which are called percentiles and which are formally defined as the value up to which you have to integrate the probability distribution in order to get the area equal to Q. So for example, one of the percentiles you know very well, it's the median. If you take Q equal to 1/2, you get the median of the distribution. But in my case, I will be interested in low order percentiles, like here, for example, the 5th percentile, which simply means that this area, this gray area is 5% of the total area below this distribution curves. And what I see when I look at these percentiles here on the left plot as a function of frequency for different system sizes, I see that there are points at which different lines corresponding to different system sizes cross. And this means that the behavior of the conductance on the right and on the left from this crossing point is different. On the right, the conductance grows with the sample size as it should be for extended states. And on the right, it decreases with the sample size as it should be for localized states. And with a little bit of imagination, you can imagine that if you are able to do the calculation for an infinitely large system, you would expect that these lines go up to infinity in this right part of the plot and left part of the plot, and they go down to 0 in the middle between these dashed lines. And the crossing points, they still stay in the same places. So if I zoom on one of these crossing points, I really see that lines corresponding to different sizes cross. And I can also use this crossing to characterize the critical behavior near this localization transition by using what people call the single parameter scaling hypothesis. That is to say, I assume that my dimensionless conductance is a function of the single parameter, which is the ratio of the system size to the localization length. And simply from this fact, I can fit this data with this expression by assuming some power law expansions as a function of the argument. And I can determine the critical exponent nu, which turns out to be of the order of 1.5, which is the critical exponent expected for the Anderson transition in the orthogonal symmetry class. So all this was done for the scalar model, but what was a little bit disappointing for us already 6 years ago is that if we do exactly the same analysis for light, so we take into account the polarization of light and we take into account the near field effects, which are different for light compared to scalar waves, we find a qualitatively different result. So we find that here on the right, the conductances computed for different sizes always increase when we increase the sample size. And there are any crossing point like here on the left, which means that there is no Anderson transition and there is no Anderson localization for light in this model. So this is, of course, a little bit disappointing because it means that many experiments that was done and that were in preparation at the time for observing Anderson localization of light was somehow hopeless. But we now understand the reason for this difference between scalar waves and light. And this reason comes from these near field terms that I show here in red, which are present for light, but which are absent for scalar waves. And these near field terms, they come from the dipole-dipole coupling between different atoms. And so they arise simply from the fact that sources or scatterers of light are at least dipoles. They're not monopoles, they are at least dipoles. And dipoles, as you know, at small distances, they interact differently. They interact according to one of the distance power 3 law. And this dipole-dipole coupling opens a new channel of energy transport in this system. So this new channel of energy transport is not completely unexpected because it was already sort of discovered, if you wish, by Forster, and it's at the origin of the Forster resonant energy transfer mechanism in molecular systems. And also in cold atomic system, it was already discussed in the perturbative theory by Nguyen Huizhen et al. Already a long time ago. But here we show that it's not just a correction, this dipole-dipole coupling, it really changes the qualitative behavior of the system. So how can we overcome this problem and how can we reach Anderson localization in this system? So up to now, we have proposed 2 ways to do this. And both are both ways they rely on the idea of somehow suppressing the role of these dipole-dipole interactions. The first idea is to put these atoms in an external field. So we know that if we put atoms in an external magnetic or electric field, the near field terms will be modified, and also more precisely, they will be partially suppressed. So maybe this can help to reach localization. And the second approach is to use complicated structures like photonic crystal, for example, in which the atoms cannot approach closer than a certain minimum distance. So in this case, if the atoms still stay at a certain minimum distance, the strength of dipole-dipole interactions will be limited, because these interactions become stronger when we decrease the distance between the atoms. Once again, there is a hope to obtain Anderson localization. So indeed, when we put this atomic system in an external magnetic field, and we assume that its field is very, very strong, we recover the situation that we have seen already in the scalar case. More precisely, we see that the conductances calculated for different system sizes show this typical behavior when they have crossings to points which correspond to mobility edges with extended states outside and localized states in the middle of this frequency band. And if we focus on one of these crossing points, we can study the critical properties quantitatively, and we can extract a critical exponent which turns out to be of the order of 1.6, which is again in agreement with the value expected for the orthogonal symmetry class in 3 dimensions. We can go even farther because we can repeat this calculation for different densities of atomic system and for different frequencies. So the nice thing with this system is that it's so simple that there are only 2 parameters. So there's the density of atoms and there is the frequency of light that we want to study. And there are no other parameters because we assume that the size of the system goes to infinity. And on this 2 parameter plane, we can draw the phase diagram where in this gray region, we have localized modes, and in the white region, the modes are extended. So you see that you need a certain minimum density of atoms to reach Anderson localization. And for vector light and magnetic field, the phase diagram is very similar. It's not exactly the same, but it has a similar behavior. Calculations of the critical exponent, as I told already, they give values which are similar to the scalar model and completely in agreement with what is expected for this system. So I turn now to a different possibility, which I invoked already, is to put the atoms in an external electric field instead of magnetic field. In this case, also, the near field effects, dipole-dipole coupling, are suppressed. But it turns out that this suppression is not sufficient because when I compute, in this case, the intensity of light inside a sample illuminated by a plane wave, I see this intensity decaying linearly for different configuration, different polarizations, etc. And this linear behavior is what you find from the diffusion equation, which means that light is diffusing in these systems and that there is no Anderson localization. So by combining these results for electric and magnetic field, I can make a link between the presence or absence of localization and the strength of near field effects. So in all cases, I can write my Green's matrix that describes the coupling between pairs of atoms in this general form here, where I have a coefficient responsible for the far field effects, and I have a coefficient alpha near responsible for the near field effects. And if I measure the strength of near field effects by integrating this coefficient, the square of this coefficient more precisely, over directions, I can establish that when this effective strength is smaller than a certain critical value here, I do find Anderson localization. But when this critical strength is larger than a certain critical value, there is no spatially localized state. So I cannot follow this dependence. I only have discrete points here because these discrete points correspond to light in magnetic or electric field and also different transitions. Because when I put atoms in the field, I destroy the degeneracy of the transition. So I have 3 different transitions, but I have no points in between because they do not correspond to any realistic physical situation. So, and finally, in the last 2 minutes, I will tell you a couple of words about localization in photonic crystals. So this is another way to restrict the strength of near field interactions because now the atoms cannot be close together. And of course, this idea of using disordered crystals for Anderson localization of light is very old. It was proposed by Sergei Skipetrov a very long time ago and has been also studied by many other authors. So what happens here is that if I show the density of states of this system, so this plot is a little bit complicated, but the idea is that the black line is the density of states for the perfect crystal, and the other lines, colored lines, are for disordered systems with different degrees of disorder. But you see that in the perfect system, you have a band gap. And when I introduce disorder, I do it by displacing the atoms randomly from the positions in the crystal. This band gap tends to close, but still it exists when the disorder is not very strong. When I look at the eigenvalues of my Green's matrix, I see that in the disordered crystals on the right, these eigenvalues, they behave very differently from the perfect crystal on the left. So for the perfect crystal on the left, when I go from the first figure where the size is 40 inverse wavelengths to the larger size, I almost see no difference. So you see that pictures are almost equivalent, which means that not much happens when I increase the size of the crystal. But in the disordered crystal, I clearly see that when I increase the size, I get more of these localized states with large lifetimes, low decay rates here, and also large inverse participation ratios that measure the degree of localization of the state. And also you see that these states, they appear near the band edge of the crystal. The band edges are shown by these dashed lines. So to perform some quantitative analysis of this system, I again compute the dimensionless conductance and the percentiles of conductance. You see again that there are distribution of conductance that are similar to what I have seen in completely random systems. And by analyzing the crossing between lines corresponding to different system sizes, I can extract the critical exponent of this transition. Again, by using the finite size scaling analysis with a single parameter scaling hypothesis, which means that I assume that all my lines, all my dimensionless conductances only depend on the ratio of the system size to the localization length. So when I extract this critical exponent, I find a value which is quite different from 1.6 expected for completely random systems, and also in general for any system that belongs to the orthogonal universality class. So this is somewhat surprising because generally it is believed that the critical exponent only depends on the symmetry of the system and doesn't depend on any details. So here, for example, there is no any symmetry, any particular symmetry which is broken. In particular, time reversal symmetry is not broken. So I would expect to have the same critical exponent 1.6. But on the other hand, we know that values of the critical exponent of the order of 1 or even smaller have been already measured in experiments, in electronic experiments. And also they have been predicted recently in calculations and were attributed to hybridization between impurity bands and propagation bands in semiconductors. So it's possible that the same hybridization takes place here because the band of impurity states that appears due to disorder in the system inside the band gap is not clearly separated from the band of propagating states on the other side of the band edge. Yes, so what is different between this crystalline system and a completely disordered system is that these localized states, they appear near band edges for arbitrarily weak disorder. So there is no notion of a critical disorder that is needed to get Anderson localization. Even a weak disorder will introduce localized states. And even more, when I increase disorder, I will lose Anderson localization, as you see here. So I increased the disorder a little bit, and you see that the lines corresponding to different sample sizes do not cross anymore, so that I cannot identify the critical point and the mobility edge. So this is quite different from the fully disordered systems in which I need to reach some critical disorder to reach Anderson localization. And then when I increase disorder, typically I get stronger and stronger localization. So in conclusion, I hope that I convinced you that Anderson localization of light can be achieved in three-dimensional ensembles of cold atoms only if special efforts are made to suppress near-field effects. And these special efforts, they include strong magnetic fields or photonic structures with a photonic band gap. So the critical exponent that I find for the diamond lattice of atoms, for the photonic crystal of atoms, turns out to be less than 1.6 expected for the orthogonal universality class. And this is something that still remains to be explained. And finally, it turns out that in these photonic crystals, there is an interesting interplay between near field effects, band gap formation, and Anderson localization, because it turns out that, for example, the disappearance of the band gap coincides with the disappearance of Anderson localization. And also this is related to the strength of near field effects in the system. Okay, thank you very much for your attention.
Thank you, Sergei. Questions? I will start because I'm just
I have one. I have one also.
Okay, well, let me start anyway. I wonder, here you're focused on 3D, right?
Yes.
If you go to 2D, is there any hope that, I mean, you could expect that maybe if you take scalar wave in 2D, vector waves in 2D, then you go back to something like a bit more than 2D, and maybe you find an Anderson transition.
So the difference between 1D, 2D, and 3D is that in 1D and 2D, you can decouple different polarizations. So in 2D, you can excite either in plane or out of plane polarization, and it will not couple to the other one.
Oh, they are totally decoupled? Okay.
So starting from the wave equation, you can decouple them. So it means that you end up with two scalar problems, which are not identical, which are different. And actually, there is a paper by Robin Kaiser and co-authors where they have studied these two-dimensional systems, and they have shown that the waves which are polarized in plane, they actually are not localized. So there is no Anderson localization in 2D if the polarization is in plane, for the same reason as here, because of this.
Because of this near field effect. Okay.
Yes, exactly.
Because it's not so that's very different from anything linked to this dimension of the system. It's really linked to this near field effect. Okay.
Yes.
So who had a question? Alain?
Moi, Alain.
Go ahead.
Okay, so yes, Sergei, I'm surprised that you put all the effect of the absence of localization in the near field effect. Why, for me, intuitively, as you know, I am not a theorist, I am an intuitive guy. And intuitively, I had the feeling that the fact that light is a transverse vectorial wave is absolutely crucial, because as you say, in 1D or 2D, we can fully decouple everything. But in 3D, because it propagates in oblique direction, then the quantity that will interfere will be vectors which are not parallel to each other. And we know that interference is efficient. We know that since the famous experiments from Arago, Ampere, and Fresnel, and other. We know that interference is efficient only if the polarizations are parallels. So my intuitive understanding of the difficulty, not to say more, of having localization in 3D was strongly linked to that geometrical consideration. And you seem to put all the fault or all the reason on only the near field interaction. Can you comment about that?
Yes, thank you for this question, because this is precisely the question, the first question I have asked myself 6 years ago when I have found these results. And the reason is that before that, we have published several papers with John Page on Anderson localization of elastic waves in solids. And
yes.
You know that elastic waves, they are also vector waves, and even worse, they have transverse and longitudinal polarization.
Yes.
So I told myself, how can it be? I mean, it's even worse, and they still localized. So and then I did precisely the same calculation as I did here for light, but I did it for elastic waves. And indeed, you find Anderson localization for elastic waves, despite the polarization. But there, a magic happens in a sense, because the behavior in the near field is different. So the behavior in the near field for elastic waves is still 1/r as for the scalar waves. But in the far field, they have free polarizations. So I think that this having vector waves with 2 or 3 polarizations in the far field doesn't change anything. Well, it changed something quantitatively, but not qualitatively. Here, it's really about near field effects and dipole-dipole coupling.
So what you say is that this vectorial character does not suppress enough interference to avoid Anderson localization. Can I say that?
Yes, I think you can say that because, as I say, for elastic waves, you find Anderson localization despite polarization, but you should be also careful in a sense because this near field here, I mean, it's not completely uncorrelated with the far field because it's all this expression obeys Maxwell equations. So you cannot change the near field without changing the far field, which in a sense means that the near field that I write here, it conditions what you have in the far field. So it's kind of all put together, but still, I think that if you just tell me that you have a vector wave, it doesn't mean that it's not Anderson localized. It's not enough to say that there are vectors.
It's amusing because if I can make a comment, when we started to look for localization of matter waves, our really intuition was that then we were going to have a really scalar wave, and so it will be very nice. So it's an example where the intuition is not necessarily the right one, but anyway, it's good to do the experiment because at the end it works.
Sure.
Okay, who else?
I had one.
Good, go ahead.
Hi, Sergei. Very nice talk.
Yeah, sure.
And there was a publication at the beginning of the year of sort of showing theoretically light localization in hyper uniform media. Like I don't know if you the team on Del Negro, and did you see this paper or not?
There were several papers.
Yes, that's okay. So this uniform media seems to reproduce somehow in a more disordered sort of isotropic way the photonic crystal properties. So
well, yeah, this touches on an interesting question because so these hyper uniform media are random media. They are not crystals, but they have band gaps.
yes.
So a related question that one can ask. So for example, in the system that I consider, what is important? Is it the band gap or the periodic structure? Because you can have a band gap without a periodic structure.
Exactly.
Well, I cannot really answer this question, I mean, because it's all sort of related, but I can tell you that indeed in hyper-uniform systems, there was a recent paper by the group of Frank Sheffield also. So they demonstrate that they can imagine a hyper-uniform system in which one finds a localized state near a band edge. But I mean, what I wanted to say is that for me, it's a little bit different story in the sense that this is not at all the same story as if you have a completely disordered system, because you only need a very weak disorder and you get these localized states. Because I mean, it's not like reaching extreme disorder and hunting localization as people did up to now. It's a completely different regime.
Okay.
So.
Okay, understand.
Sorry, my microphone was off. Sorry, Jacqueline, you had one?
No.
No? Okay, because your microphone is on. I'll mute it. Okay. So are there other questions? Okay, so if not, we move on and